In this video, I'm going to help you understand the limiting reactant and balanced chemical equation investigation that was done when we mixed two chemicals and got a gas to come off. The gas exerted a partial pressure, and that pressure increased as we added more of one of the chemicals. In this case, the chemical that was fixed was sodium hydrogen carbonate, and the chemical that we added was acetic acid. The acetic acid reacted with the sodium hydrogen carbonate to produce carbon dioxide gas and water. The question we ask is, does any mixture of moles of two chemicals give a chemical reaction? So our experimentation was with a sodium hydrogen carbonate and acetic acid. The acetic acid was made to be 0.40 molar, that is 0.40 millimoles in every milliliter. The hydrogen carbonate solution was made up to be 0.030 molar, that is 0.03 millimoles in every milliliter. And 50 milliliters of the sodium hydrogen carbonate was used in each reaction. We started with no acetic acid, and we measured the pressure that was there, the baseline pressure. Then we redid the measurement each time, adding an increasing amount of acetic acid, 1, 2, 3, 4, 5, 6, and 7 milliliters, generating carbon dioxide. We measured the total pressure and then calculated the increase in pressure that was attributed to the additional carbon dioxide being put out from the chemical reaction. This is one of the graphs of time versus total pressure that was taken by a student group. We find the pressure of the carbon dioxide produced by the reaction by subtracting the baseline pressure, which in this case was 98.57 kilopascal, from the maximum pressure. Here, with 1 milliliter of acid added, it was 99.43 kilopascal. So the difference in those two numbers is considered to be the pressure contributed by the carbon dioxide produced in the reaction. We then graphed millimoles of acetic acid, not milliliters, but millimoles, against the pressure that came from the gas produced in the reaction. And as you can see, we got an increasing, a linear increase to a certain point, and then the amount of carbon dioxide stayed flat. As the acetic acid millimoles increased from 0 to about 1.5 millimoles, the pressure of the product increased linearly. The amount of acetic acid is limiting the amount of carbon dioxide gas in this portion of the graph. So here we must say that the hydrogen carbonate, the sodium hydrogen carbonate, the 1.5 millimoles that we started with in the 50 milliliters of solution, is too big for the acetic acid being added. We say it's in excess. At 1.5 millimoles of acid, so just short of the 4 milliliter mark, the increase in gas began to level off. Therefore, here at 1.5 millimoles of acetic acid, millimoles of acid equals millimoles of hydrogen carbonate, which was initially 1.5 millimoles. We call this the equivalence point, where the amount of the two reactants in millimoles is equal. From the equivalence point on, adding more acetic acid produces the same amount of gas as before. No more gas than was put in by the 1.5 millimoles is produced when we have more. Why is that? Well, there's no more gas, just the amount produced here, produced all throughout this range, because we have used up all the sodium hydrogen carbonate ion. Now we've got more acetic acid than we need. Use of a RECA chart will help us to track the reaction down at the ionic level as we add each milliliter of acetic acid. Here's our chemical reaction, and you can see that all the coefficients are 1. The hydrogen carbonate, the acetic acid, 1 to 1, producing 1 mole of water and 1 mole of carbon dioxide per mole of the hydrogen carbonate and acetic acid, and leaving 1 mole of acetate ions. The RECA chart shows the reaction, the initial moles before a reaction occurs, the change that happens in the reaction, and the number of moles that are left after the reaction. So let's go to that. Here is our reactants and products on the R line, the reaction line. And we're going to add 1 milliliter of acetic acid. Now, the molarity, the millimoles per milliliter, is 0.4. So if we multiply that by 1 milliliter, we get 0.4 millimoles. That should say millimoles. So let's see how much we have to begin with. Well, we have 1.5 millimoles of sodium hydrogen carbonate. That's what we have in every one of the flasks. And we have added 0.4 millimoles of the acetic acid. We have no water or carbon dioxide or acetate to start with. This is the initial amounts. The reaction then proceeds. We know that we added 0.4 millimoles of acetic acid. So we can't react any more than that, and that will react with only 0.40 millimoles of the sodium hydrogen carbonate. It will produce the same amount of water, carbon dioxide, and acetate ion, 0.4. We then subtract and add those numbers to the initial, and we see that in the end, in the 1 milliliter flask, 1 milliliter of acetic acid added, we have 1.1 millimoles of the hydrogen carbonate left, we have no acetic acid left, and we produce 0.4 millimoles of water, carbon dioxide, and acetate ion. That means that the sodium hydrogen carbonate is in excess. We've got more than we need, and the limiting here in this first flask with 1 milliliter of acetic acid is the acetic acid. We now add 2 milliliters of acetic acid to the next flask of sodium hydrogen carbonate. That means 0.8 moles of acetic acid, millimoles, is being added. Well, we still have 1.5 millimoles of sodium hydrogen carbonate, but now we react that with 0.8 millimoles of the acetic acid. Of course, there is none of the product to begin with. The change? Well, now we have 0.8 millimoles of the acetic acid, so we can react that with 0.8 millimoles of the sodium hydrogen carbonate and produce 0.8 millimoles of all the products. We do the additions and subtractions, and we see we now have 0.7 millimoles of the hydrogen carbonate ion left. The acetic acid is exhausted, and we now have 0.8 of the products. We are still in a position where the hydrogen carbonate is in excess and the acetic acid is limiting. However, we're getting close. If we add 3 milliliters of acetic acid, now we have 1.2 moles. When we do the reaction, we're going to lose 1.2 millimoles of the hydrogen carbonate and 1.2 millimoles of the acetic acid, producing 1.2 millimoles of all the products. We do the additions and subtractions, and we've seen that now we have 0.3 millimoles of the hydrogen carbonate ion left. We've used up all the acetic acid and produced 1.2 millimoles of the products, but now, although we're still in excess with the hydrogen carbonate, we only have 0.3 millimoles left. We're still limiting on the acetic acid. In the flask where we added 4 milliliters of acetic acid, we notice that that's where the graph flattens. Let's see if we can explain that. Well, here we have added 1.6 millimoles of acetic acid, but we only have 1.5 millimoles of the hydrogen carbonate ion. Well, when we take away the 1.5 millimoles, we're left with some acetic acid. We produce 1.5 millimoles of the product. So now we have no hydrogen carbonate left. We do have some acetic acid, 0.1 millimoles, and that means that we flipped. Now the hydrogen carbonate ion is limiting and the acetic acid is in excess. That's why the graph flattens. And when we add 5 milliliters of acetic acid to the next flask, we still have no more hydrogen carbonate, so that's all that reacts, and that's all the product we get. But now we started with 2 millimoles of the acetic acid, so we have 0.5 left over. But the amount of product is still the same. We are still limiting on the hydrogen carbonate, and the acetic acid is in excess, but now we've wasted even more. We add 6 milliliters of acetic acid. Look, the numbers are doing the same thing. We increase the acetic acid, but we haven't increased the reaction. We haven't increased the product. The same carbon dioxide is coming off, and so the graph continues to be flat. And the same thing happens with 7 milliliters of acetic acid. We are limited by the sodium hydrogen carbonate, and therefore we never produce any more than 1.5 millimoles of carbon dioxide. And if you look at the graph, we can add 8, 9, 10, 11, 12, 100 milliliters of the acetic acid from this point on. We will never get any more carbon dioxide because it's the sodium hydrogen carbonate from this point on that is the limiting reactant.